in today's presentation, we're going to focus our energies primarily on two use cases around reducing lap times with Formula One racing. My name is Darrell Rittenberg. Let's go ahead and get started, and I'll walk through our agenda for today. We'll try to keep our introductions to a minimum. I'll introduce Tecplot, the company. I'll introduce our speaker for today, and he will tell us a little bit more about Karalit and their technology. We'll learn more about the immersed boundary CFD strategies. And then our problem for today will be looking at race car aerodynamics. We'll be looking at a Renault race car, specifically looking at shifting wing position, rear wing position, and the impact on the external fluid dynamics. We'll also be looking at a use case where we'll look at internal ventilation of the engine compartment and looking at flow through that compartment and the resulting cooling. We'll also have two live demos. We'll actually be able to walk through the problem set up in Karalit, and then there will be a demo of how to analyze those results in Techplot. So let's go ahead and move on. So a quick note about Techplot, the company, founded in 1981. We are currently located in Bellevue, Washington. There are about 50,000 users of Techplot around the world. We have, I think at this point, we're actually up over 115 academic site licenses. About me, my background, I did my undergraduate work at the University of California, Los Angeles, or UCLA, and my graduate work with Joel Miller at the University of Utah, primarily in chemical physics. I spent a year and a half or so also in Osaka doing research on certain chemical physics properties, and postdoc at the University of Washington. Enough about me. Let me introduce today's speaker, and then I'll be turning it over to him. Just real quick about our company. Our mission is to help engineers see. Data is getting more complex. We're working on strategies to make it easy to explore, discover information, and communicate results. We have three basic products. Techplot Focus is another product which is a variant, but Techplot 360EX, which is our flagship product, Techplot Chorus, which is really for looking at collections of results, and Techplot RS, which is primarily for reservoir simulation. So let me introduce our speaker for today. We're joined today by Sohail Azadai. I said that wrong, but sorry, Sohail. Good morning, Sohail.
Good morning. No problems. That's fine.
Actually, I noticed that you did your work at Cranfield Institute of Technology in the UK. I've had the opportunity to be there. You've also worked as a consultant for some years in both aerospace aerospace energy and AEC/BE sectors. You were chief engineer at Atkins Technology, and you're currently the director for UK and Ireland at Karalit. Good morning.
Good morning. Thanks very much, Darrell, and good morning, everybody.
I'm going to give you the mouse so you can click through the slides.
Okay. Thanks very much. So if we get started, just to give a bit of a background about Karalit. Karalit is a new startup with some very interesting technology for CFD. It was founded as a spin-off of a research center, CRS4, in Italy. The founder of the company is Marco Mulas, and he led the fluid mechanics department at this research center, which was founded by the European Commission. The capital is provided by a pool of investors, and the company is in Italy. It has offices, key offices in Italy, UK, and Germany, and we have channel partners that we are globally working with in order to reach the market, wider market. The company has strategic partnerships with research, academia, and industry, and there's been quite a bit of interest, about this new technology. So the Karalit CFD technology is based on immerse boundary or immerse boundary methodology, and essentially it's a simple, very simple approach to directly connect with the CFD with CAD geometry, taking away essentially all the time-consuming and the effort-intensive part of meshing that's involved in particularly complex CFD simulations, and whilst at the same time maintaining the important values of the CFD simulations, that of robustness and accuracy. There are three main, I guess, drivers about Karalit CFD. One is that we call it mesh-free because you don't actually spend any time, or you hardly spend any time creating a mesh. However, it is a finite volume kind of approach, and you do have a finite volume grid. But we call it kind of mesh-free in codes because you don't spend any time actually doing it. We are also making great inroads, importantly, into working with dirty CADs. The technology offers us particular advantages in this area. It's also apps driven in the kind of in line with that simplicity message, in order to basically make the code work in an environment that would simplify and speed up the setups for a number of pre-designed templates or application scenarios specific to particular industry segments. And also in line with the innovative technology, we have introduced innovative pricing as well. So it makes basically large parallel computing simulations very affordable, with the software. Just a bit about what immerse boundary method is. Usually people are very new to this topic, and essentially for me it's a kind of a two-step approach. You've got a complex geometry, and you need to basically do a simulation of it on a computational grid. And in Karalit, the computational grid is a non-isotropic Cartesian unstructured grid. So two things need to be done. The grid needs to sense the passage of that complex geometry through it, and for the CFD simulation, at the locations of the geometry, or at the locations where the geometry intersects the grid, the simulation needs to know what are the boundary conditions. So if we kind of zoom on, for example, to a section of that complex geometry intersecting the grid, in immerse boundary, the grid is categorized into broadly three parts. One is the fluid part. The other is cells being intersected by the geometry, being called boundary cells. And then there are additionally ghost cells, which don't appear in traditional CFD, but in immerse boundary CFD they do. And they are part of the solution, a layer or two of them. And what the code does, and this is all automatic and in the background, and that's the whole kind of technology behind making CFD simple, is that essentially those ghost cells that they're reflected, their reflections are found as mirror points in the fluid, and during the calculation, the field values are interpolated to the mirror cells, and therefore they can be the ghost cells that are solved during the calculation can be basically set at the correct values, so that the resulting boundary condition is forced onto the calculation. So what that means is that implicitly and automatically in the background at startup during the simulation and also during the calculation. The whole process of basically absorbing the geometry and its boundary conditions in a CFD calculation are dealt with by the software. And that means that a very simple workflow emerges where you have your CAD geometry imported into into the code. At the moment, it's based on STL formats, which pretty much all CAD software export into that format. And then you set up a few parameters based on the application environment, and you go ahead and do the solution. So 3 simple steps to the workflow. And we've applied it to a number of challenging calculations, scenarios in a variety of industrial applications. And what we are finding is that the code is producing strong results in comparison with other CFD calculations. So today's webinar is about the aerodynamics of a racing car. This is courtesy of Tattoos Racing, who have provided the geometry to us and the operating conditions as well. Essentially, what we wanted to show is that how easily it is that for this complex geometry of the racing car, you can set up the base case, the external aerodynamics, and perhaps look at another case, the second case, where one drops the wing by 10 centimeters, and then you set up the calculations again and get those running. And another calculation where if one wants to, for example, bring in the engine inside and open up the belly of the car to the external aerodynamics, that would serve as cooling the engine. A note to mention that these calculations are demonstrative. They are meant to demonstrate the technology, and therefore, what we are looking at course grids in order to be able to get the thing set up quickly during a live demo. So these are the operating conditions. The car is modeled in a wind tunnel scenario, and it's at the wind is coming at 40 meters per second at ambient conditions. Excuse me. And the Karalit wind tunnel application will be used. This is one of the apps that Karalit offers. The Spallart-Almaraz turbulence model is used, and together with a gas cycle implicit solver, and a second order symmetric TVD scheme has been applied as well.
Okay, well, let me go ahead and give the presentation over to you, Sohail. I'm going to, go ahead and move this over, and so I'm going to change so we can see your screen.
Okay.
Okay, it should be in your hands. So if you hit play, we should be able to see your screen.
Yes, you should be seeing my screen now. Is that okay?
Looks great.
Okay. So just wanted to set up the base simulation initially with Karalit of the race car, the Tattoos race car. There are 3 different scenarios that we discussed, so we'll just go ahead and get ready with the first one. Initially, as you come in, you get a central window where it's used for preview and also setup. It's used for setup conditions as well. On the left side is the case management, and on the right side we've got basically one can control what is turned off and on, and then there is some facilities with a basic post processor there as well. So if we go ahead and set up a new case, and perhaps call it just XX, as you open it up, it asks you which directory you want to put it in, which folder, and also which application environment you want to use. So I'm going to go ahead and use the wind tunnel application. And what that brings is the setup menus for Karalit. I'm going to read the surfaces from a surface repository. So read the surface of the car together. Sorry, it's not this one. It's actually this one. Yeah. I'm going to read those surfaces in. And that has given me, and initially it puts the fluid volume, a kind of a default fluid block around it with some default settings for the grid where the geometry would be immersed. And what we can see is that the geometry of the car, essentially in STL format, was brought in. Okay, I'll just turn that grid off now. Separate parts of the car, they have separate surfaces associated with them. So that's pretty much all. If I wanted to do something with those surfaces, there are some additional features here that on the second and third case we will get to. We'll play around a little bit with that. But at this stage, for the base case, I've just read my surfaces in, and that's fine. With the LGR, where we set up a locally refined unstructured grid, I'm going to give it some typical lengths that I have used, typical dimensions that I've used for the domain. So this is essentially the domain that would be that of the wind tunnel that the car is sitting in. The coarsest grid setting that I'm going to use is 10 centimeters. Karalit works in SI units, and it also can work in imperial, depending how you set it up in preference at the beginning. So essentially, it's set up at the moment a coarse grid around the car, and notice that the grid is at the moment just set up in the whole block. So if I remove the surface there, you see the grid is protruding through it. I would also like to arrange that the domain would start upstream, 2 meters upstream of the car. Then I'll set up some, here in this part of the panel, it allows me to put some grid refinement parameters on the surfaces of the car. And then the LGR would actually, when it starts generating the unstructured grid, it would take note of those parameters. So these are the normal dimensions, and these are the tangential dimensions of the grid. And with these, one can control growth rates. I'm going to leave that aside at the moment. So 0.24, 2 centimeters, and 4 centimeters on the car. Perhaps on the wheels, 1 centimeter and 2 centimeters. I'm going to copy that to the other wheel. And on the wings, I'm going to put 5 millimeters. and copy that also to the others. Also, I'm going to grow 2 layers from the walls, and then this layer size, this other parameter, it's a parameter for how many layers of cells is contained within basically every category of refinement as you go from the finest to the coarsest grid. I'm going to put 2 in that as well. Additionally, I want to turn symmetry plane on, and it's going through the center of the STL box. So we're at a fluid point in terms of okay. So if that essentially that fluid point is telling me that where is the computational domain for the actual fluid in the calculation. So it needs to be it's just a point. It needs to be somewhere in the fluid domain that I'm going to use, so that the grid knows, the grid generator knows that it needs to keep the cells in those areas. Because if, for example, the inside of the car was of interest, I would need to put the fluid point in that area. And also, if the inside and outside were kind of connected through some heat transfer, for example, you would add another fluid point to the inside as well. Okay, so that's pretty much it in terms of setting up the grid, and we can go ahead and generate the grid. And as we are speaking, the grid is being generated. I'm going to go ahead and set up the other panels. So it's a turbulent flow, and it's going to be ideal gas conditions. The initial, it's going to come at a speed of 40 meters per second into the domain. So essentially, it's going to, the starting value would be 40 meters per second is appropriate. I'm going to use SA model, and with a turbulence intensity of 10% and a length scale of perhaps 5 millimeters. I'm going to turn preconditioning on because this is a density-based solver and it needs preconditioning when there is a very small degree of compress or no compressibility. That's for that in terms of setting up the fluid panel as well, essentially the flow conditions. So as you can see, the grid has been generated now around the domain. If I remove the surfaces, you can see that the fluid point controls that the grid does not protrude. The grid is outside of the car body. And also, it is a symmetric domain. The grid only exists on one side of the geometry. Okay. Let's move that back to the center again. Fine. Moving on to set up boundary conditions. I'm going to set the incoming velocity at 40 meters per second. And the outlet condition is outlet pressure at atmospheric, so on this side of the wind tunnel. And also set up turbulence intensity and length scale as well for the inlet conditions. I could set up conditions for the wind tunnel, particularly the ground region. You know, you could give it different boundary conditions. Sometimes they do that, you know, depending upon the pull of the wind as it pull of the flow as the flow is going underneath the car. However, for this demonstrative calculation, I will just leave those out for now. The surface of the car is non-slip adiabatic, and I'm going to set up all functions on those and with monitors for pressure, forces in the X direction, and forces in the Z. And what I'll do, I'll also copy that across to all the wing surfaces. Okay. The wheels I'll set up as non-slip walls at the moment. If I wanted to set them up as rotating, I could do that. You would need to give the center of rotation, and also you would need to give the rotating velocity. I'll leave it out at the moment, and copy that across to the other wheel also. And lastly, the simulation parameters. So it's an implicit solver we're using. It's a time marching gas idle, implicit solver, second order TVD, 5,000 iterations, CFL number of 10. You know, Karalit is pretty stable, so it can, right at the start, it can deal with fairly significant CFL numbers. Write the results in the log file every 50, and every 25 write out the solution file. I'm going to do a calculation with 4 chords. In 4 chords, I've just increased that to 4. I'm going to have a Tecplot output, as well as the standard Karalit output. So going to save that, and it's just warning us that the wall conditions are set at slip at the moment, and that's what we just set that up quickly like that. Okay, that's pretty much it in terms of setting up the geometry for that case. So what I'll do, I'll copy that to another case where I want to drop the wing YY and get this case running. So Karalit is running on case XX, and YY is the case where I'm going to use to drop the back wing. And this kind of gives this case is interesting because it's not actually trivial. It's a trivial movement, but it's certainly not trivial in terms of CFD, because what one is ending up with is meshes that are surface meshes that are going to actually intrude with one another. It's a protruding case of geometry. So I'm going to take the rear wing. So that's the rear wheel, wing rear, this one. Edit it. Right. Edit that. And drop that by 10 centimeters. So if you look at the wing there, and I'm purposely dropping it by 10 centimeters in order to, it's an extreme case. And, you're going to get a lot from the dirty flow of the kind of weight behind the car on the higher portion of the wing. But additionally,
so, we have a couple of questions that might be appropriate as you're setting this up. The first is, what is the biggest case in terms of cell size that you can run without wall functions, and that you've run thus far?
It's not the biggest case with or without wall function really is the same. The wall function doesn't have that much of an impact, on the case in terms of memory or the speed of the case. So the case is really you can run as big as your computer size can handle it. Karalit is set up to do parallelization. We've done over tens of nodes, and it can do over hundreds of nodes. We've got the PETC algorithms, which are used for massive parallelization as well, to achieve efficient massive parallelization when you're doing even thousands of nodes. So Karalit is able to, I think, work on that basis.
And we have another question. In terms of
wall function, it doesn't have that much of an impact. Yeah.
Someone asked a question, does it resolve surfaces like a body-fitted mesh? I don't know if you want to comment on that as well.
So now, a body-fitted mesh is where essentially the mesh is conformal to the geometry. So that's what traditional CFD is based on. You have to carve out a mesh, sculpture a mesh that actually, for example, for this geometry, it fits to all the curvatures and ins and outs of the geometry, and that's what is very time consuming. The whole point about Karalit is not to have to do that. It's not a body-fitted mesh approach. And additionally, it's a Cartesian mesh, but in an immersed boundary framework, which gives it. So if I show you the mesh on this case, for example, that we are running, you're essentially taking advantage of immersed boundary and applying the boundary conditions of the surface at exactly the right positions, but you're not actually generating a body-fitted mesh, which is very time-consuming. So in answer to that, it can model any geometry that a body-fitted kind of approach models as well, but it does it in no time, essentially, as you've seen in this case. By the way, let's
another quick. Yeah, go ahead, and why don't you finish this up? And there are a couple other questions, and I guess we'll kind of come back to those during the Q&A period, so that you can finish this up.
Sounds good. So what I'll do, I've moved the wing down here, and I'm going to generate the grid for this case. Essentially what it does, it reads the surfaces, and within a few seconds, it's going to generating the layers from the surface and also the bands between the finest and the coarsest layers of cells. And and actually in terms of the setup for this one, so it's done that, and now it's at a point where it's going to decide which are the cells to throw away, essentially the cells inside the car. In terms of the boundary conditions for this case, there isn't anything different from the base case. So it is exactly the same as the base case. We're just going to run it with the same operating conditions and setup. Or we're not going to run it this one. It will be too many to run, in one case in the demo session. But it would be essentially run with the same setups. Now let's take a quick look at the other case as well, which we got running. And what Karalit did in that case was to go through all the case setups. Essentially, it took the information from those 5 panels that we gave, and it read the surfaces. It did the surface immersions, and it's basically doing the immersion at the moment before the calculation. That's where it decides where the surface is intersecting through the domain. and it changed it kind of broadcasted the calculation onto the 4 nodes that it's going to run on. Going back to the second case, it has finished setting up the mesh for that, so we can have a look. And in this case, you can see that the mesh has been again built around the car, and interestingly, the protrusion of the wing into the car is taken account of as well. So that's all we need to do actually for that case, and ordinarily at this point we would just come back and hit run again. Now the third case of the engine, which I wanted to set up, I'm going to quickly set that up as well. Call that ZZ. And here, what I'm going to do, I'm going to read from the surface repository the engine, a mock-up of an engine that I've set up, essentially, just to demonstrate the principle. So I brought that engine in as well. And if I zoom in on the case, and and just make the outer car surface transparent, you'll see the engine inside. Okay, what I would like to do here is to just pick up the outer surface of the car and add it down, just open up those boundaries at the inlet, actually the internal, the belly of the car, to the external flow as well. So the point being that we are tying the ventilation of the engine around the engine to the external aerodynamics instead of applying boundary conditions, which one would be uncertain of, just at that phase. So I'm going to use, it allows you to pick surfaces, with various kind of features here. I'm going to use the normals feature. Right. And pick up that surface. I didn't say. Let me just try that again with the normals feature. Okay. And also pick that surface as well. And as you can see, these new surfaces have been generated in the grid. So that's the inlet and the outlet of the engine. But what I want to do is actually to throw those away. So I've just thrown those away because I want to open up the car to the airflow around. Then the other thing I would need to do is to come back here in the LGR and say what is the resolution of the grid on the engine now, because I've brought a new component in. What I'll use is the same as settings. But I'll use the same as the car itself in order to quickly kind of generate that grid. Maybe I'll actually use a bit of a finer setting. Okay, so here we will generate the grid now as well. And as it's doing that, what we need to do additionally for this case is to set up just make sure the boundary conditions for the car are being repeated because we modified the car body. It's kind of sets it back to its default boundary conditions. But with the engine, we put it, as let's say wall with constant temperatures. And let's say the wall is 400, 500 Kelvin. Something like that. And okay, it's gone through the grid now. It's generated 2 million cells. But the number of fluid cells that will be left would be something probably just over 1 million cells once it's gone through, because the cells inside the engine would be thrown away. Just gonna turn the transparency on a little bit. Whilst that's finishing up, I'm just gonna check back with my run on the first case. Okay, so it's gone through the immersion process, and now it's on the 0 iterations, and it's going to start doing the other iterations. With the engine case, it's exporting the grid now, and so at the moment it still hasn't written the final grid, but eventually you'll be able to see the final grid. Yeah, there it is. It's exited on that. There. So now you can see that the mesh inside as well as outside the car has been generated. If I get rid of the wheels, you can put a little bit of transparency on the engine as well. Okay, you can see that there was no protrusion inside the engine. Get rid of those surfaces. So what we have is the mesh around for the aerodynamics calculation around the car being tied to the flow inside the car, and eventually the flow will exit from that exhaust that we opened up. So that's all really one would need to do in terms of setting up that case before one runs it. And Durell, I guess you would be showing us the results from these cases, and just to show that yes, this case, the first base case that we set up, is up and running, and in the Karalit window it's showing the imbalance between the two sides of the equations are reducing. Essentially the conservation equation residuals are coming down fairly healthily. So back over to you, Durell.
Thank you. We do have several questions. I just want to let everyone know that we will have time to address those questions. Let's quickly review. So I'm going to quickly walk through how one can actually analyze that collection of results using Tecplot products in general, but let's talk about some of the strategies for evaluating the multiple cases. In particular, we're looking at the lowered wing geometry versus the base geometry. We'll also look at the external aerodynamics, and we'll spend a little time looking at the thermodynamics of the engine case. And I'll try to also make sure that we have plenty of time to evaluate these results as well as answer questions. So we're going to look at the collection by evaluating it in two tools. I'll show you how one can actually leverage Techplot Chorus to set up a quick project which allows you to manage the analysis of the three cases. I'll also show you how you can do simple comparative analysis using Techplot 360. And we'll try to go through this somewhat quickly, as it's more important, I believe, to actually show you the results than to spend too much time just working them up. But here is the basic geometry. So this is the results that come directly from Karalit. They output in a Tecplot binary format that can be loaded directly. So this, you can see, has the surface geometry, the wheels that Sohail talked about. Here's the rear wing. This is the base case based on its location next to the wheel. And if we wanted to quickly evaluate the fluid dynamics, we can generate a quick slice. So here's a slice that actually is in the X-plane. And I'll kind of move it quickly through the body. We're currently on that slice. We're looking at, we can look at pressure, which in this case, the contour levels that I've chosen are probably not optimal. So I'm actually going to show you both wings. So let's start with the base wing position. So here is the wing. This is the lower position, so you can see very quickly between the two, or you can compare them side by side. So we're looking at both geometries simultaneously. Because these are linked together and we're looking at the pressure field, I can interrogate the volume by merely moving the wing position. And you can see as I move that wing position, it updates automatically in both the lowered case and the base case. So if we wanted to evaluate the fluid dynamics by looking at a series of stream traces, one can do that very quickly just by generating some around the wing. So this is something that you can do quite easily. We can do the same on both cases. I can also apply a style. So if I look at the style of this particular frame and I want to apply it to this geometry, one can do that by merely copying that style information to evaluate. So you can save that style, which is the look and feel of the frame, and I could put that under the directory that we want to look at for this geometry. But as you know, we're looking at three cases, and although I could set most of this up in batch, if I want to evaluate each of the three models in context, I can use a tool called Techplot Chorus. And so I want to show you quickly how that works. So this are the three cases, and basically we have the two cases which are purely looking at rear wing position. And we also have the case which is the thermodynamics with the engine, which is radiating heat at 500 Kelvin. And you can see that I have the three cases, and how I generated those cases was actually very simple. And I'll open up the file so you can see it. So I generated a very quick index file where I put in the information about the individual solutions. I put in information that I happen to have a layout. And then I categorized them as whether or not it was primarily fluid dynamics or thermal, and determined whether it was the base case or whether or not we were looking at the modified geometry. And this is all I needed to generate a project in Techplot Chorus. And so I was able to generate a project, and what that project basically gave me was just this, which is these are the three cases. And for each of the cases, then, I can evaluate the results by bringing those open. So for example, I'll open up one of them, and I guess we'll just look at the one data file for the base. This is the lower geometry. And what that will do then, it will send the results over to 360EX, which actually I think I have to set up, so let's not worry about that at the moment. So that would give us the lower case. In this case, we're looking at the geometry with the wing, and you'll notice that, as Sohail pointed out, the geometry is actually now in the main car geometry, and Karalit did a good job with the immerse boundary strategy, allowing them to very quickly look at this complex geometry. And I know that from my experience with working in the industry now for 15 plus years, trying to generate the body-fitted mesh and make those changes can be quite an exercise. But if we want to interrogate the fluid dynamics, we can do that via a slice, and we're going to put this slice in the Z direction, and then we're going to change that slice to look at pressure. And mind you that the results are based on the pressure contours that I've put here, and I basically can generate additional contour levels just by adding them directly. But that's not really what I'm interested in. I'm more interested in the fluid dynamics rather than pressure gradients. So I'm going to evaluate the vector field by using vectors. So I can turn vectors on the surface very quickly, and you can see what the surface vector field looks like. But I'm more interested in the vector field on the slice, so I can turn that on. I'll turn off the mesh, and perhaps we can look at the pressure on those vectors. And so this is a quick way to interrogate the vector field. And because we can now access this, we can actually evaluate that vector field as a function of position near the rear wing. So it's very easy to evaluate those vectors. I'll turn the vectors off the body just so it's easier to see. I can also, if I wanted to see kind of where the slice goes through the domain, I can make the body translucent so you can kind of see where that sits. If I were more interested in looking at other surface quantities, I can do additional calculations. If I wanted to do forces and moments calculations, I could do that as well. But for this case, I'm just going to calculate an additional variable. The variable I'm interested in is going to be the vorticity magnitude. So we'll set this up. And we can do calculate on demand. The data is relatively small, so it isn't critical to set it up to be calculate on demand. If you had a large mesh, you may actually want to do that. But in this case, it's unnecessary. And we just want to make sure that we set up the fluid and reference variables. So we'll set up pressure as pressure. And for density, we'll use density. And once we have that set up, we can do the calculation. And it's going to go through now. And so we can look at vorticity magnitude, which is a nice way to look at some of the complexity of the vortex shedding off the rear wing. Okay. So there are a couple of nodes that are coming up at 0. And so Techplot will always give you a warning, but it's not necessarily critical. So as we go through this, ultimately what we're trying to do is just to understand the fluid dynamics, but we want to compare the two results. So I'm going to go back to, as this is calculating, why Techplot Chorus provides a nice solution. So I can actually grab both of the solutions, the lower and the base case, and I'm going to open those solutions, and I can take advantage of a style template where we'll just look at the rear wing with a slice. And I'll say, OK. So what's going to happen in this case is it's going to open both results side by side so I can quickly compare those results. And ideally, we're doing a qualitative compare, but there's actually, as you can see here, I'll make this bigger. So here are my two results. If I wanted to look at a slice, for example, I can generate that slice. And what Techplot Chorus provides, which is kind of unique, is the ability to synchronize that style across multiple solutions. So you can envision you may actually have on the order of 100 different wing positions that you want to evaluate. And using Techplot Chorus, one can actually go through and quickly interrogate those changes and quickly identify what might be driving the physics. OK, well, in the interest of time, I'll just, we'll do kind of the cooking strategy, which is one can then use that approach to evaluate multiple solutions. And ultimately, what Techplot Chorus provides is a way to very quickly interrogate a set of those solutions, and I'll kind of zoom in, and look for deltas. So because the engine interior is important, and I've actually turned off the surfaces in this case, this is my base case. This is the lowered. I can use my base case as a start point and look at a qualitative difference between the three solutions. And so basically, you can see what that net impact is on the pressure field when I move the wing lower. So this is kind of a very quick way to evaluate that solution. If I want to understand the overall fluid dynamics, I can evaluate multiple plots looking at everything from stream traces to pressure fields to temperature contours across all solutions. And so I can understand how a system is behaving. So this is just a simple way that one can actually evaluate the results. It's, I think, helpful also to understand that with Techplot 360EX, our newest release, we have the ability to use pages. So I've been able to build a single layout, which actually has comparison of the different wing positions, the base position versus the lower position. This is the example with the thermodynamics around the engine, and I can generate additional pages to look at just the simple geometry. And if I save this, it's going to be a singular layout, so you can imagine almost building a simple report. And because layouts are text files, you can actually automate the generation of multiple pages within a simple layout using different data sets. So, I don't want to go into too much detail on this. My plan is to actually present the detailed overview of a tutorial on how you can work with these results and post those results to YouTube. So for those people who want to try to use Tecplot in that way, they can do that afterwards. But in the interest of time, we do have several questions. I would like to start to move into the Q&A portion. Again, if you have questions about how to use any of the tools, please do not hesitate. We do have several questions, so I'm not sure we'll get to all of them before we run out of time. So if we do miss your question, we will get back to you by email. So I'm going to start with a question by Long Hee. So Hale, this is for you. It says the wall function mainly used in high viscous case in which shear stress is dominant or dominated. In the form drag dominated case, like the case you're running now, how much difference will the wall function affect the result?
It depends on I guess on which part of the car that you're looking at. You know, for this kind of a very aerodynamic shape, I think the wall function is important. For cases where essentially you've got form drag, the car or the body is serving mostly as a blockage, then the impact of the wall function and what you do near the wall is perhaps less of an issue, you know, in terms of what flow field emerges, you know, from your solution, because it's a different case where the viscosity it's unlike the viscosity kind of case at the walls impacting the solution. In this case, I think it is important because it's a highly aerodynamic shape, of course.
Mm-hmm.
So you need a good wall function.
Okay, there's another question about parametric methods such as response surfaces. Tecplot Chorus does include multiple. We have a kriging model and a simple response surface, quadratic response surface, available for looking at parametric space. So, that's primarily available in the Techplot Chorus toolset. The example here, there aren't enough data to really fit the output, but that's a good question. Another question for you, Sohail. Can you take an existing structured multi-block mesh and bring that into Karalit and reuse it?
At the moment, we haven't gone that way. We are trying to directly connect with the CAD geometry, essentially directly connect with design. So trying to go as far upstream as one can, even with concept, even to the conceptual design stage of the whole design process, if you like. Therefore, we are trying to take in raw geometry and set up the mesh. Given that philosophy, it's not that useful, for us to be able to read in, I guess, as far as I can see at this stage, reading other meshes, because you can generate the Karalit mesh very quickly from a CAD.
We do have several questions. However, we are just about out of time. So Hale, I'd like to thank you for a very fascinating presentation and an overview of Karalit. It looks like a very easy-to-use tool, and it looks like there's many applications. I guess the one last question to take us out was one around using MRF for the wheels so that you can actually have the rims moving, and is that possible in Karalit?
Yes, we've got single rotating reference frames, but obviously the wheels would need MRF. MRF is in the kind of design plan is in the development plan for Karalit, but we've got a simple solution towards that, which basically looking simpler than MRF in order application of the whole wheel, and that should be coming online, not too far from now. In terms of the existing approach, the circumferential surfaces, you can of course apply wall functions, moving walls to them, and that's what one can do currently with Karalit.
Okay. Well, we're just
thank you very much, Durel, as well for your presentation and for the opportunity here.
Yeah, thank you. We do have several questions. We will get answers to everyone's questions out as soon as possible. Unfortunately, we're out of time. Again, Sohail, thank you so much for spending some time with us this morning or afternoon, as I believe as we were doing this across the pond. I'm in Seattle, and it's outside of London.
It's interesting what technology does.
Yes. Thank you again, and thanks to everyone for listening in. The recording will be available soon. And thank you, and look forward to seeing you at our next webinar. Thank you.
Take care. Bye-bye.